Okay, here we're going to look at one of the main applications for the conservation of momentum, namely collisions. We're going to consider several different types of collisions. One type will be elastic collisions, where not only momentum will be conserved, but also the amount of kinetic energy before and after the collision will be conserved, or energy will be conserved only in the form of kinetic. We won't have to worry about other forms. Then we'll have inelastic collisions, where the only thing we can use is the conservation of momentum. Energy as a whole will always be conserved, but here that won't be a useful concept because some of the energy will be converted into forms that are hard to keep track of, like, for an example, thermal energy. We will also distinguish between collisions that take place in one dimension versus two dimensions. The key difference here is that two-dimensional collisions will have to keep track of the different components of momentum separately. We also can consider another sort of type of a collision, which is called an explosion. And this is where we have an object that is either at rest or moving at constant velocity, and it flies apart. Radioactive decay is one such example. And here we have not only the conservation of momentum, but we'll have some form of potential energy turned into the kinetic energy of the explosion. We'll start by considering one-dimensional elastic collisions. Here, the force between these objects as they collide will be converted into some form of potential energy. The force will be conservative, which means that potential energy will be turned back into kinetic energy after the collision. This allows us to use two conservation laws: the conservation of momentum, which I've laid out right here, the momentum before equals momentum after, and the conservation of energy will only be in the form of kinetic, so we add up the total kinetic before and it equals the total kinetic energy afterwards. Now, if we look at these two equations, they basically restrict what kind of outcome we can have. If we assume the two masses are known in advance, and we know the two of the velocities, like for example the initial velocities, the momentum conservation and energy conservation will determine the final outcome. The algebra is messy, and I've attached the math onto a separate sheet, so if you want to look at that, you can. But basically, don't worry about memorizing it. Usually when we have these kind of problems, the math will be set up so it'll be relatively easy. Another point to bear in mind is the center of mass of the system will remain constant. Let's consider one example of an elastic collision. Now here we're going to take one of the objects to be at rest, then take the two conservation laws for energy and momentum, solve them for the final velocities of the two objects, and these are the equations we get. Do not bother memorizing these two equations. The key thing is you need to know where they came from. They come from application of the conservation of energy and the conservation of momentum. However, here we can take and use some values where we have a 1 kilogram mass colliding with a half kilogram mass, and we can plug the numbers in and find out that the heavier mass slows down and the lighter mass speeds up significantly. Total momentum will be the same, and the energy before and after, if you plug in, will both be 2 joules. A second example would be inelastic collisions, and we'll again restrict ourselves to one dimension. Here, the forces between them will not be conservative, which means kinetic energy will be at least partially converted into some other form of energy, particularly something like thermal energy. And thermal energy will not be returned back in the form of kinetic. Energy will still be conserved, but it won't be in a form we can easily keep track of. Momentum will always be conserved, so the only conservation law we can use is the conservation of momentum. So here we have the initial momentum equals the final momentum. We still have the same 6 quantities, but now we only have one constraint. If we assume we know the two masses, and we know the two initial velocities, we no longer can predict the final velocities. We need some additional constraint. That constraint can take one of several forms. We might be simply told that the two final velocities are equal, or the two objects stick together in the collision. We could be given an impulse curve telling us something about the forces between the two objects, and we can use that information. Or we may simply be told that one of the final velocities is known. And again, like in the previous collision, the center of mass will continue moving at a constant velocity, because the forces are still going to be all internal. So let's take an example of an inelastic collision. And here we're going to assume, or more precisely, we're not going to assume that kinetic energy will stay the same. So we have two objects, again, a 1 kilogram and a half kilogram object. One of them will be at rest, and the other one will be moving at 2 meters per second. The collision will be inelastic because we're not going to assume kinetic energy is conserved. Instead, the additional information will be given is this impulse curve, which gives us the force between the two objects as a function of time. So the collision starts at 0.01 seconds, lasts another 0.02 seconds, and then the collision more or less is over because the objects are no longer interacting. Then what we want to do is find the final velocities of the two objects. What I'd like you to do is take a few minutes and solve this problem. First, the hint is find the area under this force time curve. That will give you the impulse that one object exerts on the other, which, as we already showed, is the same impulse the second object exerts back on the first. That will give you the change in momentum of each of the objects. Once you know that, you can then figure out their final velocities. So we can use the conservation of momentum. The initial momentum is all in the larger mass, and it equals the sum of the final momentum. But we also can use that the impulse is the area under this curve, and that gives us the change in momentum of each of the objects. In particular, it gives us the change in momentum of the red object. And since it starts with no momentum, that is also the final momentum of that object. The area under that curve is the area of this triangle, which is 1/2 base times height. The base is 0.02 seconds, and the height is 100 newtons. So that means the area under that curve is 1 newton second. That means that equals the final momentum of the red object. Its mass is 1/2 kilogram, so therefore it must be going at 2 meters per second. Once I know that, I can use that in the conservation momentum, because I now know that this is 1, this was 2 to start out with. That tells me the final velocity of the second object must be 1 meter per second. So the heavier object slows down from 2 meters per second to 1 meter per second. The lighter object starts at rest and ends off moving off at 2 meters per second. We can then take and show that this is an inelastic collision by calculating the initial kinetic energy, which is 2 joules. And the final kinetic energy is the kinetic energy of this 1/2 its mass times its final velocity of 1 meter per second plus 1/2 times this mass times its final velocity squared. That gives us a total of 1.5 joules. We started with 2 joules, so we lost kinetic energy. Some of the energy was turned into heat. Another case we can consider is a 2D collision. In this case, we'll consider, for an example, a 2D elastic collision. The way we can always set this up is pick our frame of reference so that it is attached to one of the objects. So therefore, one of the objects could always be treated as it being at rest if we use our frame of reference to be the velocity of that object. It will then be at rest. We then orient our x-axis to be along the direction of the remaining object. That means that we will have no momentum in the y direction, and that's just for simplicity. So we can use conservation of momentum in the x direction, which now is all of the momentum of the moving object, must be split into the momentum of the two objects after the collision. There is no momentum in the y direction, so these two must add up to 0, which means one of the angles must be negative. And then we have the conservation of energy in the form of kinetic energy, because in this case we're being told that it's an elastic collision. So then we have this final equation. So we now have 3 equations. Notice here we actually have 4 unknowns if we are more or less to assume the 2 masses are given and the initial velocity is given. And what we want to do is predict the outcome of this collision. We can almost do that. We have 4 unknowns. We have these 2 angles and the 2 magnitudes of the velocity. That means we need an additional constraint. One of the things we could just be given as a value for one of the velocity, one of the final outcomes. We could be given one of the angles or one of the velocities. Or we could be told exactly how these 2 objects collide. For an example, if they are in fact circular, we could be told exactly where they hit. That will then give us the contact force will be perpendicular to the surface, and that will give us the direction of the force, will give us the direction of the changes of momentum. That could then be used to uniquely determine the outcome. Let's consider an example of billiard balls. And the advantage of billiard balls is all of the masses are equal, and generally speaking, one of the masses, in fact, does start at rest on the billiard table. So we'll take here a cue ball right here colliding with the 8 ball. The cue ball is moving with some initial velocity. afterwards both of the balls are flying off in different directions at different speeds. We will treat the collision as an elastic one. And what we want to do is predict what is the final outcome. Well, first we apply the conservation laws. The conservation of momentum means the mass times the initial velocity of the cue ball equals the sum afterwards. But all the masses are equal, so that means the velocities themselves must add up. We can then add on the conservation of kinetic energy. And again, all the masses are equal, and all this factor of 1/2 is in every term. So here we get actually the sum of the squares must add up. Notice, the first conservation of momentum tells me that these three vectors must form a triangle, because this vector, which is one side of a triangle, must equal the sum of those two, which would form the two other sides of a triangle. The conservation of energy is then the Pythagorean theorem for that triangle. Namely, this would be the hypotenuse, and these would be the two sides. That means the angle in between these two vectors must be 90 degrees. So this is the kind of vector diagram we have to end up with. This is the initial velocity, which is the hypotenuse of a right triangle, and these are the two sides, and this angle up here between V1 and V2 must be 90 degrees. Now, another example we can consider, which is of historical importance, is beta decay. That's a form of radioactivity. And we could consider this example of where a carbon atom turns into a nitrogen atom and emits an electron. The electron was originally called beta radiation until people realized that it actually was nothing more than an electron. We can treat the carbon nucleus as initially being at rest, and then it ejects these two particles. This one right here is actually called an antineutrino. This is the electron, and here's the nitrogen nucleus. If it's initially at rest, then that means the total momentum was 0, and the final momentum must add up to 0. The energy comes from some form of potential energy being converted into kinetic energy. Here it's because one of the neutrons in the carbon atom turns into a proton in the nitrogen nucleus, and the proton is a little bit lighter than a neutron. So what we're actually seeing is some mass being converted into energy via Einstein's E equals mc squared. There's where the potential energy is coming from. When people did this analysis, originally they didn't know that neutrinos existed. So the equations they wrote down were these less the last term. When they did that, they realized that these two momentums have to be equal and opposite, and that actually constrained the outcome to be unique. Namely, the electron should have come up with one and only one amount of energy or momentum. When they did the experiment, rather than the electron coming out with a unique value of energy and momentum, it came out with a range of values. The value they calculated was actually the maximum amount of energy that the momentum had, that the electron had. This was puzzling because that means that generally speaking, in beta decay, neither energy nor momentum was being conserved. This was very puzzling until someone proposed maybe there's a third particle being emitted, and that third particle actually carries away the missing energy and momentum. And that particle had to be electrically neutral because in this reaction right here, charge had already been conserved. And because energy was close to being conserved, whatever this is carrying off probably doesn't have a whole lot of mass in it. So it was a very light, almost massless, electrically neutral particle that escaped detection. And that particle was called the neutrino. And it was eventually discovered, and therefore we realized that in fact energy and momentum is always being conserved, even in the beta decay, and the missing amount of energy and momentum was carried off by a new particle. This is how it was discovered, the neutrino.